Hi, it's Moser, back with a brief tutorial on molar gas volume and the ideal gas law. By the end of this video, there are three things that you should be able to do. You should be able to use a balanced chemical equation to predict the volume of a gas produced in a reaction. You should be able to determine the volume of any gas at standard temperature and pressure, or STP. And you should be able to use the ideal gas law to determine the temperature, volume, pressure, or number of moles of any gas. Things you already need to know how to do, how to calculate molar masses, and how to perform basic stoichiometric conversions. Okay, let's go. So during that whole golden era of quantitative chemistry in the 1700s, Guy Lussac had been looking very carefully at gas volumes. Perhaps you'll recall that one of the gas laws was actually named for him. And what he found was that when you took 2 liters of hydrogen and 1 liter of oxygen gas, you formed 2 liters of water vapor. 2 to 1 to 2. This volume relationship of hydrogen, oxygen, and water. Oh, goodness, that looks an awful lot like the coefficients in the balanced... Wait a minute. Those are the coefficients in the balanced chemical equation for the reaction of hydrogen gas and oxygen gas to form water vapor. Well, yeah, it was. And what he found was that all the reactions that he looked at that were a gas reacting with a gas, forming a gas, followed the same pattern. What this led him to conclude was that, in fact, at constant temperature and pressure, the volumes of gaseous reactants and products are just the ratios of small whole numbers. And it turns out those ratios are expressed by the coefficients in the balanced chemical equation. This is called Guy Lussac's law of combining gas volumes. Now, all that aside, this makes one thing super easy for you. Look at this equation. Look familiar? It's the combustion of methane. These things are all gases when they're reacting. The methane, the oxygen, and all the products are gaseous. As long as you have a reaction in which every single product and reactant is a gas, you don't have to worry about a darn thing, because the volumes of the gases are in their perfect ratios that line up with the coefficients. Let's do a sample problem involving the combustion of methane. So we're asked, if 6 liters of methane combust according to this reaction, how many liters of water vapor will be produced? Do I have to know the temperature at which the combustion is happening? Do I have to know the pressure under which it's happening? No, because the beautiful thing is, as long as everything is taking part in the same reaction, it is all at the same temperature and the same pressure. So the volumes are just ratios. Here's how you do it. We can use the balanced chemical equation to show that when 6 liters of methane combust, for every 1 liter of methane that combusts, 2 liters of water will be produced. Therefore, we get 12 liters of water vapor. This works as long as everything's a gas. If you have anything that's a liquid or a solid, this is right out. Okay, well, let's revisit something we've talked about before with gases. Aha, this is from the previous chapter. We looked at all these relationships between pressure and temperature, pressure and volume, temperature and volume, and you know that as pressure increases, temperature increases, as temperature increases, pressure increases. Pressure and volume are inversely related. When pressure increases, volume decreases. When the volume decreases, the pressure increases, or decreases. And we know that temperature and volume are directly related. So when temperature increases, volume increases. When volume increases, temperature increases. When one decreases, they both decrease. Okay, well that's all fantastic. That assumes one thing, and it's sort of the elephant in the room. We haven't really talked about it. The thing it assumes is that you aren't changing the actual number of particles, the number of moles of the gas. Well, what happens if we need to know how many moles of a gas we have? Gases are really hard to mass. They're very hard to confine and mass. They tend to be very, well, spread out. They're not very dense. So wouldn't it be handy if we had some other benchmark we could use? Aha! Well, it just so happens, it turns out, that if we put any gas at standard temperature and pressure, that's 1.0 atms and 273 Kelvin, or 0 Celsius, any gas at STP, 1 mole of that gas will have a volume of 22.4 liters. It's really pretty remarkable. So it doesn't matter if we're talking about O2 or N2 or CO2 or methane. The list goes on and on and on and on. Any gas at STP, standard temperature and pressure, will have a molar volume of 22.4 liters. What does this allow us to do? Well, for one thing, it allows us to start to think about reactions where not everything's a gas, and it allows us to use this 22.4 liters at STP as a way to figure out how many moles of a gas we've produced. Hey, that's pretty slick. Let's talk about this reaction. Magnesium and hydrochloric acid yield aqueous magnesium chloride and hydrogen gas. Well, we're going to collect that gas somehow, and we could use the lost mass method to figure out how much of it we produced, but that's really not all that exact. If we can measure the volume of the gas that we've produced and use our combined gas laws to get that down to STP, well, then with the volume we've got, we can figure out how many moles of gas we've produced. Let's try it. Having produced 2.7 liters of H2 at STP, how many moles of hydrogen gas were produced? Same thing, we're going to do as a factor label. Our given, of course, is the measured volume of hydrogen gas that was produced. Our conversion factor is the 22.4 liters of H2 at STP, which is equal to 1 mole of H2. I put the at STP in here so that I don't screw up, because if you're doing this at anything but STP, you can't use this conversion factor. I've got a raw answer of 0.1125 moles of H2, and since I only have 2 sig figs, that will become 0.11 moles of H2. Now, I don't have to write at STP on this, because now I'm just down to talking about the number of moles of H2. At this point, I can do anything else I need to with that. Convert it to a mass, though we don't do that as often with gases. Okay, let's quickly touch base and review. You should be able to use a balanced chemical equation to predict the volume of a gas produced. As long as everything's a gas, those coefficients serve as the ratio of the volumes. You should be able to determine the volume of any gas at STP. It's 22.4 liters at STP for any gas in the whole universe, and you can use that as a conversion factor. Now, the last thing we want to talk about is the ideal gas law. So remember, we said that the combined gas law worked really well as long as we didn't change the number of moles. As long as we're dealing with a consistent number of molecules of the gas, we can look at the relationship between temperature, pressure, and volume. But what if we do change the number of moles? Oh. The ideal gas law is just a mathematical relationship, and while the old combined gas law connected pressure, volume, and temperature, the ideal gas law connects pressure, volume, temperature, and the number of moles. If you want to derive it for yourself, page 341 in your Holt Modern Chemistry book has the entire derivation, but most people aren't so interested in that. They just want to know that PV equals nRT. So you can probably figure out that P is pressure, V is volume, T is temperature, in Kelvin, of course. N is something that we've only used occasionally, but it means number of moles. R is a little bit more mysterious. It's a constant. That's a number that we plug into an equation again and again. You could call it a fudge factor, but this one's really not. Let's look at R, the ideal gas constant. So R is equal to 1 atm times 22.4 liters divided by 1 mole times 273.15 degrees Kelvin. What that works out to is 0.008 0.05784, are you ready for the units? Liter ATMs over mole kelvins. We typically round the ideal gas constant to 0.0821, but those units are really important, and I tend to write those down because if you are using different units for pressure, then the ideal gas constant changes. And if you want to see, there are 4 commonly used ideal gas constants. Look on page 342 in your Holt Modern Chemistry textbook. Let's look at an ideal gas law problem. A sample of CO2 occupies 3.5 liters at 10 degrees Celsius and 1.02 ATMs. How many moles of CO2 are in the sample? Note that this is not at STP. If it was at STP, we could just use the 22.4 liter conversion factor, but it's not. So we need to use the ideal gas law. PV equals nRT. Let's list our variables. This is very reminiscent of the combined gas law. I've listed my pressure, volume, and temperature. The number of moles, or N, is what we're going to be solving for. And R, what's R? 0.0821 liter ATMs over moles Kelvin. Note that when I wrote the ideal gas constant, I actually put in the units, liter ATMs over moles Kelvin. You'll see how helpful that can be in terms of doing the dimensional analysis to prove that your algebraic rearrangement of the formula is correct. So, let's go ahead and rearrange to solve for N. If I divide both sides by RT, I've got N isolated. Let me move a few things around. I've plugged in all my variables, and I've put the units in with everything. What that allows me to do is ensure that all my units are canceling as expected. So, if I do a quick check, ATMs divided by ATMs, that cancels. Liters divided by liters, that cancels. Kelvins divided by kelvins, that cancels, which means I'm going to be left with moles. And hey, that's what I'm solving for. Pretty cool. Let's get a raw answer. I got a raw answer of 0.15365,214 moles of, and this would be CO2. I'm limited to 2 sig figs, so I'll be keeping that and rounding based on the next digit. So my final answer is 0.15 moles of CO2. Okay, that's it. You'll have some practice problems. Get going.